introduce the
Whereas if that attribute infinite set of possibilities.
You better look. I guess because you've been gone.
We'll probably have to pick it up and pick it up.
All right.
Yeah.
Oh, exactly. I wanted to ask before, so
Yeah.
then. Yeah, no, they're sponsored.
Hello.
Yes. Just today.
Yeah.
Yeah, good to see you again.
Volunteers should be maximum
Oh, spread apart.
spread apart.
Not in this area. Like a panel.
So people know who to look for.
Yeah.
Kevin.
Yes. The name tags were seriously delayed by the construction. UPS did not know how to get into the building. Arrived.
Where are they?
They're out by the probably.
Know where Luke is, but okay. Well, I guess we'll start. We'll just shame Luke for not showing up yet. When he comes in, everyone point and say he's late. No. So we're gonna start the algebraic tutorial. We have all my co-presenter Evan here and all of our wonderful TAs who will be helping you during the exercise sessions. Please ask them for help, otherwise they'll feel sad and lonely. Let's get started. AlgebraicJulia. So this tutorial is going to be in 3 parts.
Do you want to introduce us by name?
Oh yeah. All right. That one's Kevin, Tyler, Chris, James, Angeline. And then when Luke comes in, we'll point at him. So this is going to be 3 parts. I'm going to do the first part, and then Evan is going to do the second 2 parts. After each part, there will be an exercise session, which is mandatory. So the first part is just about like the general vibes of AlgebraicJulia. So a question that we get a lot is, why are you doing category theory in Julia? Why are you leaving the nice, happy land of Haskell, OCaml, Agda? Why? And there are a lot of reasons for this, but I'm going to start with the less adversarial reasons. So first of all, James appreciated that. So the Corey Howard correspondence makes a connection between typed lambda calculus, which is like what is implemented. Oh, here's Luke, he's late. Makes a connection between typed lambda calculus and Cartesian closed categories. But like applied category theory is much bigger than Cartesian closed categories, and computer science is much bigger than typed lambda calculus. So this is not the only God-given way of doing category theory on a computer. There are like lots of categorical things which can be implemented without working in a faithful implementation of the typed lambda calculus. So the things that we do in CATLab, among other things, are mostly like databases, dynamical systems, computer algebra. All of like databases and dynamical systems, having mutation is really useful because you want to mutate your databases and you don't want vectors in your dynamical systems to be linked lists. And then also the third thing is computer algebra, where having dynamic types is useful. Anyway, so what is Julia? Julia is a programming language that is dynamic. Now, people often think dynamic means you don't have types. That's not quite right. You have types in a dynamic language. It's just that syntactic variables don't have types. Only values have types. What else is Julia? Well, Julia is fast. So carefully written Julia. You can write Julia, which is not carefully written, and then it'll be slow. But you know what you're gonna do. But if you're careful, you can be competitive with C or Fortran, and a lot of scientific like infrastructure, like modeling systems, etc., are being rewritten in Julia and from C and Fortran. So there's a lot of momentum into the Julia scientific ecosystem. Julia is dynamically typed, but it's also dependently typed, which is weird, but it makes sense. Like values don't have, or variables don't have types, only values do, but the types of those values can depend on other values. And the idea behind this is that like it's essentially like attaching metadata to the value that allows for the compiler to use. I don't know. And finally, it looks like math. You know, I want to just write dot product like that. I don't want to have to, you know, remember something that's not like math. I don't want to have to like put public static void main stuff. I just want to write stuff that looks like math. And why Julia? Well, it was the original sort of motivation was for Julia was it was built to solve the two-language problem in scientific computing, which is that you had anytime you wanted something to go fast, you'd write it in a low-level language, and anytime you want something that was easy to use, you'd write a high-level dynamic interface in like Python or R. We don't say the MATLAB word when we're talking about Julia. But the thing is that interfacing these two languages is like really complex. You have to know much more about like runtime systems than you want to. So Julia, you can just do it all in one language. You can have your high-level dynamic slow stuff, but then have it seamlessly attached to your low-level stuff because it's all in the same language. Okay, so now we're just going to go over a couple example programs for what does Julia look like. So here is an implementation of the Euler algorithm for integrating a vector field. So this is like solving an ODE. The parameters that you're getting here are an implementation of the vector field, which takes in a vector and returns a vector. It's just, yeah, that's what a vector field is. Then we have an initial state, a time increment, and then number of steps to run for. And it's pretty simple. We just make a matrix, an m+1 by n matrix, which is going to store the path that the solution is taking. We're going to initialize the first row of this matrix to our initial state, and then we're just going to run a for loop with the update of the Euler algorithm, and then finally return the path. Notice you don't have to write return. It's not Java. And so what are some notable features of this? Well, I want to point out that first of all, there's built-in numerical linear algebra. I never want a language where matrices aren't built in. It's really annoying. Second of all, auto-broadcasted arithmetic. So I can just multiply a vector by a scalar. It's fine, it works. Finally, yeah, oh yeah, and add vector. I don't even think about that anymore. It's just how it works.
Just what plus is.
It's just what plus is. And then finally, it's syntax that is, familiar to if you use Python or MATLAB. It kind of looks similar, but like, of course, slightly better. So now we can actually use this. We can take a cannonball. Famously, cannonballs travel in parabolic trajectories, and we can solve Newton's law with velocity and gravity. And when we plot the trajectory of this, it's a nice parabola. So two things to note here. This is an anonymous function that we're using for the vector field. And plotting is really easily. You just pass in the vector of x's and the vector of y's, and it plots. Okay. Now so that was like nice numeric code, but I said Julia can do like numeric code and sort of dynamic code. This is more dynamic code. We have an abstract syntax tree here for like simple calculator expressions. Here we're using a feature of Julia called multiple dispatch, where based on the operator, this is using like the dependent typed feature of Julia, based on the operator that you put in as a type parameter, you dispatch to call a different function. Here we are broadcasting, this is like a map, evaluate over the arguments. So this recursively argument, this, AV system shutting down, please wait. No, I don't want. I didn't touch anything. But it happened recently, apparently.
It happened in that one recently.
Okay, now it's great.
Oh, we need this one.
Shut down by the man.
Yeah, MathWorks heard about this. So we also have first class symbols. These are nice. These are like strings, but faster. And yeah, so I'm going to move on from this, but you can experiment with this more in the exercise session. So where is Julia? You notice a pattern. What, why, how, where? Well, here are some links. The slides are on acttutorials.netlify.app, so you can click on these links there. And finally, before I finish this session and have the TAs help you install Julia on all of your computers, what does it mean to do category theory in Julia? Well, we can just do category theory. So we can implement a category by just making a type for the morphisms and a type for the objects, and then implementing two functions, ID and compose. Now, this is not very principled. In CATLAB, we have a more principled way of doing this, where we also say like, okay, what is a category and what laws should it obey? But this is what it boils down to. And so this is FinSet. We can also do FinVect. In FinVect, the objects are these structs, and the morphisms are matrices. Here we get the identity matrix, and here we have matrix. What?
Go ahead, and I'll ask.
Okay, and here composition of functions is just matrix multiplication, which is with times. Yeah, what's up, James?
Why didn't you just call I?
Because I wanted to show, like, I wanted to write the loops. Yeah, I mean, I think this double for comprehension is actually kind of cool.
Yeah. You're showing off so many features. You've got nested for loops in a comprehension
Yeah,
that's statically typed,
yeah,
that is also using the ternary operator.
yeah.
So good. This is like a CS 101 final exam question. What does this code do?
Yeah, I mean, but you can sort of read what this code does. It's just like it goes for each I and for each j. If I is equal to j, then it's 1. Otherwise, it's 0. That's an identity matrix. Yep. Cool. And then here we have a fancier version, which Evan added, which allows you to do matrices over any number field. So integers, rationals, complex numbers, whatever you want. Cool. So that was the end of part 1. Now, open your laptops, go to the website, and do the exercises.
How to do that.
Yes, I will pull them up, but also you should, yeah.
It's going to escalate quickly. Operats and SMCs.
Yeah. Oh, that's not. Exercises are here.
I did bring my laptop.
So yeah, so you can see this URL.
If you didn't bring a laptop, you should probably sit next to someone who did.
A few comments about the exercises. There's a ton of them in here. And coding takes a long time, even if you're very experienced. So there's no expectation that you'll work through all or even most of them. The idea is to just give you a flavor. You can approach them how you like. Like you could try yourself. If you get stuck, look at the solutions and try some more, or pick and choose which problems appeal to you. It's really up to you how you want to approach it. So, and then the TAs are available to help if you get stuck. Yeah.
Start.
Raise your hand if you want any help. Very nice.
My dynamic, like.
No, install Julia.
It's loading. But I just wanted to. Yeah.
Just give me shit. All right.
Justify. I'm not saying it's bad. Like I can justify it. I really like.
Yeah, so
Well, you have types in Julia.
Well, like,
I mean, just environment. Yeah.
like
Yeah,
I really.
In some of the slides you were
so if
Ideal, but like.
good question. If you have questions about the Unicode characters, you just do like /alpha tab, and it makes the Unicode. It's LaTeX. So whatever the LaTeX name for a character is, that works. And then it's like BBR.
No, you're right.
Instead of like math BB
But like that's not
R,
really.
it's just like BBR.
Alright, that's nice.
One thing is, dynamic typing is really.
Can you do that in source code files that you write to outside?
Yeah, I do.
Yep, source code files and the terminal.
There are,
That's nice.
but there are.
Yeah, that's actually how I did it.
Characters into my computer.
Open the Julia REPL /BBR highlight paste.
Tiny. Just do ending bracket and then just do.
Unlike
That is not such a kind of
Are you ready to?
come back. Did it take you that long to get to your hotel room?
Yeah. Like in Python where it's.
Oh, because you came back here and then.
Yeah, I made a mistake.
Yeah, so
Either like. There are ways to set up separate environments with like.
and I know I ended up doing both of the course.
I'm just checking.
Oh, yeah, you could also.
For me, when I was trying to install which doesn't allow you to
Just do like once you get the
that was my
like as if you're typing LaTeX.
yeah.
Thank you.
Yeah. Oh, anyone else? Does anyone else here run NixOS?
I'm the only next class user right now.
You already have NixOS people.
You're not the only one.
There are 3 Nixers in the audience.
NixOS is a.
We'll have a NixOS people.
We'll have an NixOS tutorial next year.
A package manager operating system. So Nix is the package manager. NixOS is the
Like if they were here.
that allows you to install by symlinking them from your current runtime environment to solid like Nix store, which has like the hashes and very rapidly switch environments. INV on steroids, and that can manage every package.
Oh, so this has made. Now.
That should really file. Have a run screen. Restarting usually helps with
Yeah,
this.
like go back into your terminal. Activate.
One thing that is cool is you can
Yes.
So that's supposed to drop you to. Works with any so
Do you have any other questions?
got a very wide vocabulary, so
Try that.
oh, so which would be try opening
I could do that too, actually. Yeah, maybe.
Table like just down, there's like a visually identical table. The latest
okay, so
long-term support, you probably tried to download long-term support because you use Linux and you like things that are supported.
I honestly wasn't trying anything.
So just unjar that into your home directory and put the bin folder on your path.
Okay.
And you're done. The executable is in that bin. And you're on glibc. So you click the glibc.
Yeah,
You're not as Try it. If it crashes immediately, download the
way,
I'm pretty sure.
It breaks your computer.
Yeah.
smart idea.
no, two computers
Making,
no, I mean the exercise.
Oh, this.
Yeah,
Oh, are you thinking about running back to it is your hotel?
the default information folder, at least I'll get the percentage.
Yeah,
Gigabytes and eat too
I'm just saying, so where do I download AlgebraicJulia?
Everything is inside the exercise document, so I'd navigate there, expand, and have Julia yet? It's because it's
Yeah, that's the first.
and then, yeah, I'm not sure.
yes, yeah, for any reason.
Okay, so you're on the Ubuntu, so yeah, you can probably just install them through the package.
I was taking the journal up.
For sudo apt install Julia. I think it's apt space install because I guess apt, yeah. Yep, try that and then enter your password and then that should.
Like we will not some switches are being presented.
Let's see, try pressing up and then tab.
There's only like 20 minutes.
And then tab.
And then I think
Tab
the push
twice. Let's see. Delete the space and then press tab. So try apt search Julia.
the best way to get Linux binaries is still
Okay, roll up.
I mean, it still have like notations.
Let me try to look up.
I mean, you can certainly get Julia for Hello World without forking it there.
Oh yeah, let's do it from the website. And so yeah, I'd probably just install it from the website because like it's probably not up to date and do generic on x86.
I mean, I can't do this. This is what I can do.
Like those commands in the console.
James tried to put me on.
that's like
And then, so yeah, in the tutorial, there's a subject called franchise.
Oh, okay.
So if you go to that,
Okay, so right click on the short text.
I wonder if it hates excellence. I don't know, I also had, I was running. Oh, right. Yeah, my phone's ringing. Now, if you're starting to get a ruffle, I mean, it's in my house. You should have brought that. Yeah, I have not like that's hardcore.
Okay, let's start wrapping up. We're going to do part 2 of the lecture part, and then after that, we've got a coffee break.
You can just like add a Julia file.
Oh, so that's not
Yeah. So if you want, you can just
Okay, so hopefully you at least managed to get Julia installed and tinker around a little bit. So we're picking up again now, getting more into the category theory content specifically. So in this part of the tutorial, we're going to talk about dynamical systems and how you compose it, both reviewing some of the math that you may or may not already be familiar with, and also illustrating how these ideas manifest in AlgebraicJulia. Okay, so in compositional or categorical systems theory, it's useful to separate some notion of an interface for a system, so how the system is going to interact with other systems from the systems themselves. So there are different ways of making that formal, but one way to think about it that's very common in the community is to think that you're working in a particular kind of monoidal category, like maybe it's trace monoidal categories or hypergraph categories. And then systems would be particular categories of that kind, or rather they would be the morphisms in those categories, and then you compose them together. Another way to think about it that we use a lot in AlgebraicJulia is via operads and operad algebras. So from this point of view, an operad tells you the kind of ways that you can compose the systems together, and then an algebra for the operad are a particular class of systems that can be composed in that way. So some examples of operads are directed wiring diagrams or undirected wiring diagrams. And we're going to see some algebras of those. Now, the point of this whole way of thinking is that by abstracting away from particular systems to the kinds of interfaces that they can have enables reuse of ideas. Not just in mathematics, which is a theme of all of applied category, but in the software as well. We want to build on these abstractions to make software that's more general than people typically do. So getting to dynamical systems, this community has worked a lot on this set of ideas, and I know of several different ways that one can think about composing them. Quite possibly there are others. The first one is as resource sharers. So I'm using, I think, Sophie Lipkin's terminology here. So in this way of composing, we think that systems expose some part of their state, and you compose them by identifying are gluing together along that shared state. And so this is a sort of undirected notion of composition. There's also a more directed notion of thinking of dynamical systems as so-called machines, where we think that the outputs of one system get plugged into the parameters of another. So this is sometimes formalized as using like lenses and that sort of machinery, and it's a more directed notion of system. And then you can even put these together. So for the sake of definiteness and focus, we're going to hone in on resource sharers and the different sort of tools we use to implement those in AlgebraicJulia. But we also do other kinds of dynamical systems as well. Okay, so what are these resources sharers? So we're going to work in a continuous setting, so we're thinking of them as systems of ordinary differential equations. What they expose along their resource or interfaces are sort of resources, and you compose, as I said before, by identifying or gluing or sharing these resources. And in terms of the notions of interface we were talking about before, researcher sharers are going to end up forming a hypergraph category. That's if we're thinking in terms of monodal categories, or if we're thinking in terms of operads, they're going to be an algebra of the operad of undirected wiring diagrams. So it's really this latter approach we're going to be mainly highlighting. We're going to be looking at undirected wiring diagrams. So a little interlude here about how we work computationally. So in mathematics, it's typical to think of functions as sort of black boxes. You put in inputs, you get out outputs. That's all that you can really say about them. This does not suffice for many computational purposes. You really need to know what's inside that box. You need to be able to introspect on it and understand something about what it's doing. When computing, we're typically honing in on some smaller class of functions or morphisms that are introspectable. So a few examples of introspectable morphisms might be functions between finite sets. These are really simple because you can just write them down explicitly what that mapping is. Another example is linear maps between finite dimensional vector spaces, because those can be cashed out as matrices. Unlike a lot of the more formalized approach is to doing category theory computationally, we focus on concrete computations. And so I'll contrast these two views in the two ways we might think about resource sharers. So a natural thing for a mathematician to say would be that we'll just think of an interface as being as a space, whereby space I maybe mean something that's nice enough to have a tangent space. We might think it's a smooth manifold or something like that. And then our resource sharer on that interface would consist of another space, which is going to be the state space, a map from the state space to the interface, which is basically you think of as exposing some part of the state via the interface, and then finally a vector field as a map from X to the tangent space on X, a section of the tangent bundle. So this is a nice sort of abstract way to think about that stuff, but it's not something you can immediately compute with, because how do you represent an arbitrary space? How do you represent an arbitrary smooth map? So, at least there are maybe all sorts of ways one could think of getting to a more concrete representation, but we're going to be working with maybe the simplest one, where we're going to look at Euclidean spaces. So now for us, an interface is just going to be a finite set, and so we're going to think of it, the elements of that set, as being ports or as interface variables, and then this finite set is a symbolic or a combinatorial representation of the Euclidean space R to the I. And then similarly, resource sharer now has a finite set of state variables. And the exposed function now goes from I to S, so that's the other direction. So we're thinking that often this would be an injective. So we're thinking that we're exposing some subset of the state variables via the interface, and then finally there's a vector field there. Okay, so to give an example of this, one sort of simple model, which as we'll see can be a building block for making a bigger one, would model the predation on of one species on another one. So maybe foxes eating rabbits. So geometrically we might say that both the state space and the interface space are just R2. Symbolically, we'll give ourselves some variables that represent those coordinates. So like F for foxes and R for rabbits. And in either case, we can write down a vector field. So we don't need to have much structure on the vector field, because really the only thing we need to be able to do with a vector field is evaluate it. That's all you need to do when simulating the system. So we can get away with a black box sort of perspective there, but we need to have more details about the interface and state space. Okay, so here's another example. I think I'll go ahead and skip this one. I want to get to what's this starting to look like in AlgebraicJulia. So the resource sharers, as well as other kinds of dynamical systems, are available in a package called Algebraic Dynamics. One of the things this package exports is called a continuous resource sharer. So this is an implementation of the thing that we've just been talking about. So here we're seeing how we can make one of these. So we're going to create one for this predator-prey interaction, where the system's going to have 2 ports on its interface. It's going to have 2 states. It's going to expose both those states. That's what the 4th argument here is. And then the 3rd argument is actually giving the vector field as an anonymous function. And then the rest of this code is just showing how we can plug that into an ODE solver to see what the dynamics looks like. So here, because there's no birth or death process associated with this, we're just getting that the prey is eaten and the predator population is growing until both of those saturate. Okay, so moving to the next topic, the way we're going to be composing resource sharers is via undirected wiring diagrams. So I'm going to talk a little bit about that, and then we'll break, and then in the 3rd part, we'll finally put all these pieces together to see how resource sharers are an algebra for the operand of undirected wiring diagrams. But let's just start with undirected wiring diagrams. So quite a intuitive notion. There are boxes, there are junctions, they're connected together by wires, and then some junctions are exposed. I'll go in a bit more detail on that, but we can see right away how you can make one of these in CATLAB. We have a Julia macro. So a macro in Julia is a way of reinterpreting Julia expressions that doesn't use the normal semantics of the Julia language, but lets you capture that expression and then interpret it in a new way as you see fit. So what we have here is a miniature domain-specific language for defining a UWD implemented as a macro. And so we're first declaring what are the variables that will be on the outer ports, and then each of these lines is declaring a box, as well as what junctions its ports are connected to. So, yeah.
Why is that called the relation macro?
because the way this syntax is what people often write for relation. So this doesn't have to be interpreted as a relation, but like people would often write like A, X, comma, Y to mean that the relation A holds at the elements X and Y, and then this whole thing would represent some conjunction of different assertions. So it's like a lot like a conjunctive, like it's basically like the conjunctive fragment of a relational calculus. And in fact, the logic of UWDs is closely related to regular logic, which is the fragment of logic in which you have basically conjunction and existential quantification and stuff. So that's kind of where the name comes from, but certainly not all of the algebras for this operads are relations, although relational composition is one of them. Any other questions before we move on? Yeah. Okay, great. What operating system are you on? Just install it through your package manager, it'll work. Oh, wow. Okay.
It works, and then like I'll reboot my computer.
Okay, yeah, we can help with that IT issue later, but I'm surprised that that doesn't work better. Okay. Okay, so there, we've just seen sort of the intuitive way to look at UWDs. But mathematically, it's nice to think of them as cospans of finite sets, where the left set in the cospan is partitioned up into several different subsets. So the way we think of this is that the junctions in the wiring diagram, these black dots, are the apexes of the cospan. The outer ports are the elements in the right foot of the cospan, and then the left foot of the cospan is a disjoint union of sets corresponding to each of the boxes. And we'll see in part 3 in more detail why this is a useful point of view. Composition of undirected wiring diagrams is closely related to the way that cospans compose. But for now, I'll just point out that this gives kind of a way to define wiring diagrams as a co-presheaf or a C-set. It suggests sort of a schema for that, and that's useful for us because, as we will explore in the exercises, CATLAB has good support for C-sets or categorical databases, or however you want to think about those. So from this point of view, we can say that a UWD is a functor into FinSet from the category freely generated by these objects and arrows. So we have a set of junctions, outer ports, and ports. Those form the cospan that we just saw. And then moreover, there's an arrow from port to box, which is telling you which of the boxes inside the diagram the port is associated with. And that is giving you the partition of ports, or the partition that we saw here on the left side of this cospan. So the schema kind of comes from that view of wiring diagrams as cospans. So as I was saying, we have generic infrastructure for C-sets in CATLAB, and UWDs are implemented that way. And we can, so you can construct them directly by manually adding the different stuff, but as I was saying before, this relation macro is a convenient way to write a specific one down. Okay, so that's it for part 2. We've got a few minutes left until the coffee break. I can take any questions now. and then we can pick up with the exercises for this part when we get back. Are you gonna? Yeah.
So the C set, adding the box, the arrow from the box, just like.
Yeah, okay, good question. So, yeah, this is sort of the difference between like thinking of a collection of sets indexed by another set or just one set sitting over another via a map, and like this map from port to box. And often this sort of, the index point of view is often more intuitive. Like it's more natural to think that a box has a set of ports assigned to it rather than thinking of the set of all ports mapping to the set of boxes. But the advantage of this sort of bundle or fiber point of view is that like it all, you don't have to add any other categorical or algebraic gadgets to your schema to describe this. So you can describe this just using the bare structure of a category, whereas if we want to describe it in another way, we would need to have a more expressive schema language.
Problem of nested.
Yeah, so Owen's last exercise is for one of you to help him solve that problem. So if you're feeling especially ambitious.
Come up with a theory of nested adjectives. Good first issue.
Any other questions? Yeah, okay, it looks like we're starting the next thing. Anyway, so we'll pick back up with the exercises for part 2 when we get back. Thanks, everybody.
I don't know. I do this.
I guess well, that's
Never had this problem on ours. That and many other problems. That's true. Less opinionated. Right. Yeah. Just install your OS and describe it.
Oh, yeah. I don't know. Maybe it was just early in the morning. But I mean, all I mean to say is like this.
We actually. I'm not sure actually.
The container doesn't like wax under there.
how are you
I'm installing now these,
packages?
Good to know as well. Thank you.
That's like a local integration of things.
It should be, right? Because it's just like a simple like language.
how do you know AlgebraicJulia?
So I'm curious about the project. I've been a Julia hobbyist for quite some time, and So, like, I guess my undergrad was in physics, and then I found, like, I guess Jupyter Notebooks was a primary tool, which were formerly IPython notebooks. So, and Julia kind of like so scientific computing is in my background, and then I guess, but so was type theory. So I guess type theory got me into the Wi-Fi.
pointers.
Yes, I'm using it.
Yeah, OM semester. I think again with what I said before. Yeah, so and I just ended getting the product up there. I get two more. And now.
Okay, so we're gonna pick back up again with part 3. So, we've seen dynamical systems as resource sharers, and we've seen UWDs. And so in this last part, we're going to try to bring those pieces together to see how you can compose resource sharing dynamical systems. Okay, so to put it very glibly, the sort of thing that we want to do is we have a composition pattern, and then inside each of these bubbles or boxes, we want to put one of the dynamical systems and press a button that says compose to get a larger system out. So this is a general sort of pattern. The particular example that we're looking at, the systems are going to be resource sharing dynamical systems, and the composition patterns are undirected wiring diagrams. So UWDs fit into a kind of categorical structure, and that structure is an operad. So we're now going to talk a bit about operads in their algebras. So in an operad, so people might say a typed operad, but for us operads will always be typed, also known as a symmetric multi-category. You have a set of objects, which might be called types, and you also have morphisms, which in the operatic context are thought of as some kind of operation. The word operad comes from operation. But these are generalized compared to categories in that the domains of an operation are not a single object, but a finite list of objects. And so we think of operads as formalizing a kind of hierarchical composition like we see in this charmingly drawn cartoon, where we imagine that a UWD is a kind of operation whose input, with an input for each of its boxes, and then the outer ports define its output, and we compose them hierarchically by plugging a whole UWD with compatible output ports into a bubble in another one. So that's what this picture is showing. And there's a connection between operads and symmetric monoidal categories, which we will not discuss all the aspects of, but what we'll mention is that you can certainly get an operad from a symmetric monoidal category, and the way that you do that is you say the objects of the SMC becomes the types of your operad, and the inner operations in your operad are given by morphisms in your SMC, where the domain of the morphism is a monoidal product of if in different objects. So what really is the point of talking about this if we're going to see that you know, the operads that we're using come from SMCs? Well, the thing that's nice about operads is they provided an intuitive and unbiased syntax for specifying composition. So if we were to think of resource sharers as forming a hypergraph category, and I say here are 5 resource sharers, compose them, you've got to break that down into a bunch of, you know, products and binary compositions and all this stuff that is really sort of inconvenient to think about. So we like to use operads in their algebras on the computer because it's a really nice sort of syntax for you know, domain workers to specify their models. And then it's also sometimes convenient to use SMCs in the mathematics just because that's such a central concept in the field that's very well understood. So it's really useful to be able to sort of move back and forth. Okay, see if I can make this. Okay, so we're going to make an operad of UWDs in this way. So we're going to start with the category of cospans. So the objects in this category are finite sets, and the morphisms are cospans, or if we're being careful, they're equivalence classes of cospans up to isomorphism. And you can pose them by taking pushouts, as shown in this picture. So this is the composite of a cospan from A to B with a cospan from B to C. And this category of cospans inherits a symmetric monodal product from the coproduct in the category of finite sets and functions. And, you know, remembering from last time the cospan viewpoint on UWDs, we can see that in the operad induced by this SMC, the operations are precisely UWDs because they're cospans of this form where the left foot is a sum of given finite sets. Right, so hopefully we remember that from the last part. Okay, so that's how we make an operad out of UWDs. Now, the next ingredient that we'll need are operad algebra. So operads give you the syntax for composing, algebras give you the semantics. So we want to get to how resource sharers form an algebra for this operad, but first let's talk about what an operad algebra is. So given any operad, an algebra for that assigns to every type in the operad set. So those are like the set of things of that type. And then for every inner operation, it defines a function of in arguments that says how you perform that kind of composition. So that's the data of an operad algebra. And then in order to actually be an algebra, this assignment of functions needs to be well behaved. It needs to preserve the composition and the identities and the symmetry operations that you have in an operad. So in terms of the pictures that we have in mind when drawing UWDs, these sets parameterized by the types of the operad or the things that we're going to put in the bubble, and then these functions are the instructions for how to compose them together. Okay, so we want to make a cospan algebra, and it's convenient to separate this into a couple steps. We can so there's a general construction for making UWD algebras that lets us sort of factor this problem a little bit. So cospan algebra is a lax symmetric monoidal functor from the SMC of cospans into a set with its Cartesian product. So this concept has been studied by Fong and Spivak, and what they show in their paper is that it's equivalent to hypergraph categories, and we're going to see. And so spelling that out is kind of a longer story, but we're going to see here how this is closely how this gives you a UWD. So as part of being a lax monoidal functor, this thing has the so-called laxators. So this is a family of functions parameterized by lists of finite sets that goes from a product of the sets evaluated at F to a single one on the sum of the sets. And given such data, we can make an operad algebra. And the way that we're going to do it is that given a UWD of the form shown here, we're going to associate the function that first applies the laxators, which we think of as just sort of like putting all the different systems next to each other. And then using the action of the functor on the cospan itself to give you the second part of this morphism. And so at least if you look at the signature of this, it type checks. That's the sort of thing that we're supposed to give in an operad algebra. And it turns out that it will satisfy the right laws in view of the laws of a lax symmetric monoidal functor. Okay, so this is the busiest slide in the presentation, so sorry, but we're gonna go through it. And so we're really into the meat of things here. We're gonna define the lax symmetric monoidal functor that will give you resource sharers. So, or at least we're gonna sketch how this goes, and once we've done that, by applying the machinery that we just saw, we're going to get our operad algebra. Okay, so for the first thing we need to say is like, what does this thing do on objects? So given a finite set that we're now thinking of that as the interface for the resource sharer. So we're going to send that finite set to the set of all resource sharers with that interface. Okay, so next, we're going to give the laxators. So for that, given some interfaces in different sets of interface variables, and then given resource sharers on those, we need to send them to a resource sharer on the interface, which is the coproduct or the sum of all those interfaces. And well, what do? There's really only one thing that comes to mind, which is, well, I'm just going to basically stick all these resource sharers next to each other with no interaction. Basically, we're going to just take the disjoint union of them in some sense. So we're going to take the disjoint union of the state variables. We're going to then take the disjoint union of the functions exposing those, and then finally, we'll take the product of the vector fields. Okay, and so now for the most involved part where the actual resource sharing is going to happen, we need to define what this lax functor does on morphisms. So given a cospan, we're supposed to get a function from resource sharers to resource sharers. So if we sort of unpack that, what we need to do is say, given a cospan, say from I to I prime, and a resource sharer on the interface I, we need to make a new resource sharer on the interface I prime. And how are we going to do that? Well, this is where the gluing or the sharing is finally going to happen. So we are going to set up this push out down here where and I'll unpack on the next slide a bit more what's going on in this, interpret that a bit more. But taking it as it is for now, that also gives us a map from the, so the new state variables will be given by this push out, and we'll also get a map from the old state variables into that, and then we'll use that to form a new vector field. So let's start to unpack a bit more what's actually going on there. Okay, so what we're doing in this push out is just saying that any two state variables that are connected to the same junction via their interface are going to get merged together. That's what this push out is doing. And then having done that, we've got to take our old vector field on the state variables S and get a new one on the state variables S prime. And so, and all we have to do that is this function F that goes from the old state variables to the new ones. So what do? We start by taking vectors on S prime and precompose with F to get something in R to the S. Then we have the original vector field, which goes from R to the S to R to the S. So we can apply that. And then finally, we need to get back to R to the S prime. And we do that by pushing forward along F, where we're basically summing up all the things in all the coordinates in the pre-image of the target coordinate. So intuitively, what's happening here is that when the state variables associated with several different researchers get merged together in this coproduct, each of those has some contributes to the overall derivative in that vector field by just summing them up. So each resource sharer kind of contributes to that derivative. Okay, so that was a lot. That was an overview of the math, but now we're going to see the payoff by seeing this actually in action. So we're going to make, this is still a small example, but it illustrates the point of compositionality. So we've got 3 different small dynamical systems. One which will represent the growth of the rabbit population. So this is just going to be some exponential growth model. One representing the predation interaction between rabbit and foxes. So that's the one we saw before. And then finally, a system representing the exponential decay of the fox population due to them dying off. So each of those gets to be a continuous resource sharer. We saw last time how we can define those. So this is the same sort of story. Now we're also creating here the UWD that corresponds to this composition pattern. So what are we going to do? It's quite intuitive, right? We've got the rabbit population appearing in both the growth model and the predation model. So we want to share that resource of rabbits. Likewise, we want to share the resource or population of foxes between the second and the third models. That's what this UWD is encoding. Okay, and then we worked hard to get here, but now we get to do all of that stuff happens here in one line. So we're going to say we have this UWD, RF, we're going to apply this composition pattern to our list of 3 component dynamical systems. So OApply is supposed to stand for something like operatic apply, like it's invoking the algebra of this operad. And that gives us a new dynamical system which we can simulate, and already, even though this is a relatively small dynamical system, we can see some interesting qualitative behavior. So, you know, we are starting out with a very small population of rabbits. So the fox population is dying out due to starvation, and then the rabbits are growing though, and their population is growing, and that gives the fox population something new to eat. So it starts to growing more rapidly, and eventually there are enough foxes that they're eating them at a faster rate than the rabbits are growing. The rabbit population starts to decline, and then the fox population starts to decline after that. And so you get this oscillating behavior where both the rabbit and the fox populations are oscillating but offset from each other. Okay. Yeah, so that's it on that. I have a incomplete list of references here. So yeah, I know that was a lot. Happy to take any questions. And then in the last part of the session here, we'll be exploring the part 3 exercises, tying all this stuff together. Thanks. Great. Okay, well, let's start the exercises. Thanks, everybody.